Hello and welcome back. We are going to look at essentially the last set of topics for the course, which deals with thermodynamic cycles. So, we will first go on to the basic Rankine cycle and then we will look at the Brayton and the basic vapor compression cycle. So, the Rankine cycle is essentially used in power plants for producing power from say thermal sources such as say coal or natural gas powered plants where you would heat water. Of course, most gas power plants would use the Brayton cycle instead. It's also used in, for example, nuclear power plants where you heat water and then use the water to get work. So, over here this slide shows, for example, it shows a power plant in some fashion. So, over here for example, what it shows is a boiler or a furnace where you put in fuel, you take air from the environment and burn the fuel. It could be, for example, coal or lignite or something like that, and then we get hot gases. The hot gases transfer heat to steam, to liquid water, which is essentially coming into this, to convert it into steam. That steam is expanded in either one turbine or two turbines to get work. These hot gases, which after transferring heat to this liquid which is flowing through these pipes, are sent out. They are used sometimes to preheat the ambient air which is coming in, and then they are sent out. Since they may have some unwanted substances like say oxides of sulfur or nitrogen and so on, they are sent to pollution control devices where some of these are removed, and then they are sent to a stack where they cool, and then finally you are left leaving out relatively clean combustion gases, which will of course have a lot of carbon dioxide and water vapor as the main constituents. The steam which is coming out through this boiler is sent through a turbine. The main turbine is shown here. From the turbine, it comes out as low pressure, low temperature steam. It is then sent to a condenser. From the turbine, we are extracting out electrical work. We saw that a turbine is a device which can convert enthalpy into rotation, rotational movement of a shaft. That shaft is connected to an electrical generator, and we are extracting out electrical work from this, which is then used to power lights and fans and whatever else we want. So, the low pressure, low temperature steam coming out of the turbine is sent to a condenser. The idea of the condenser is that it takes the steam which is coming in and converts it into liquid water, which is now at low pressure. This water is pressurized in a pump, and if we want to add some more water, we add it here. Otherwise, the same water can go in a loop, and then we have another pump here, and then it sends it back to the boiler. If we have two turbines of this kind, what we can do is we can have some amount of expansion in the first turbine, send it back, and then send it to second turbine. What we can also do is some of the substance from this we can remove here, and the rest we can remove here. But essentially, in the simplest form, we could think of it as a system with one boiler, one turbine, one condenser, and one pump. And for condensation, we need something to cool the steam which is coming here, which means we are taking out heat. So, that is usually done by means of a circuit of this kind. So, we have chilled water which is sent through a pump through this condenser. It exchanges heat. This is a heat exchanger. It exchanges heat with whatever is coming here, and this water is now going to become hot. We need to cool it. What is often done is this is sprayed. As it sprays, some of this water will evaporate, and in evaporating it will take latent heat and cool the rest of the water. So, the liquid level here will come down a bit, so we can add makeup water and keep this in sort of a constant level. And this is essentially a cooling tower where this process happens. So, in a simpler form, we can think of it as being a system of this kind, where we have a boiler where we are adding heat. So, this would usually be from burnt products of combustion, but we are not going to worry about that part of it right now. We are only going to look at whatever is here within our system. This is for our case a closed system. So, there is steam coming in the boiler. As far as this liquid which is coming into the boiler is concerned, there is liquid here which becomes steam in the boiler. The same steam goes through the turbine, gets expanded. The same thing comes through the condenser and the same thing goes to the pump. So, if I take the substance which is here or here or here or here, sorry about that, it is essentially the same substance which is undergoing all of these processes. So, we have in this case a closed system which can exchange energy. In the boiler, if I consider the boiler as a control volume, then it is an open system where I have something coming in here, something going out. Similarly, if I consider the condenser as a control volume, I have something coming here, something going out. Similarly, if I take the turbine as a control volume, I have substance moving through it and I have substance moving through the pump. But if I take this, all of this put together, then the mass is constant and I can consider it as a system where the mass is fixed. So, this is essentially the system which we are going to look at in some amount of detail. The same thing is shown here with different parts for the boiler. So, over here we have a pump which is taking in low pressure, low temperature liquid. In the pump the pressure is increased. So, we have high pressure, low temperature liquid coming in here. It is sent to a boiler. The first part of the boiler is usually called an economizer. The second part is called the boiler itself. The third part is called the superheater. We will look at why these are called in this fashion. And then we have high pressure, high temperature steam coming out. This high pressure, high temperature steam is expanded in a turbine and we get at the end of the expansion process steam which has low pressure and low temperature, but it is still largely in vapor form. We send it through this condenser over here to convert it into liquid form and then we are left with low pressure, low temperature liquid. So, this liquid is now pumped up, it once again becomes high pressure and then we once again send it through the boiler and convert it to steam and so on, and this cycle goes on in a cyclic fashion. So, this is essentially the process which we want to look at. Why we arrive at this particular process, we can look at in a little bit of detail by drawing what would be essentially the Carnot cycle. So, let me go back to here. We discussed that the Carnot cycle is essentially the most efficient of the cycles from the Carnot's theorem and the second law. So, the Carnot cycle consists of two isothermal processes, this one and this one, and two reversible adiabatic or isentropic processes, this and this, which are supposed to be straight lines parallel to the t axis. If I want to get work out of this cycle, I would run it in such a way that I add heat at a high temperature, reject heat at a low temperature. So, this would essentially be my Carnot cycle. I can label it as some 1, 2, 3, 4. As we recollect from earlier, 1 to 2 is essentially reversible adiabatic process which is compression. 2 to 3 is an isothermal process where we have heat addition. 3 to 4 is a reversible adiabatic process where we have expansion, and 4 to 1 is a reversible isothermal process where we have heat rejection. So, in 1 to 2 we are doing work. This would be done in a compressor in the case of a Carnot cycle. In 3 to 4 we get work which would be done in a turbine in the case of a Carnot cycle. 2 to 3 and 1 to 4 would happen in isothermal heat exchangers where we are transferring heat to the cycle over here and removing heat from the cycle over here. So, this is the ideal cycle and this is what we would like to use. But what we also discussed is that there are practical problems in using this cycle. So, one of the problems is that it is very difficult to transfer heat at constant temperature. If I have, for example, a gas and it is in single phase, if I want to transfer heat, I need to have a temperature difference, otherwise it is very difficult to transfer heat. So, the kind of process 2 to 3 is not feasible in a single phase substance. So, if I have only liquid or only gas, this is very difficult to do because as I transfer heat, the temperature tends to increase. So, it is extremely difficult to do. So, what we can do is now put this into a two phase region where we have the process happening at constant pressure, because constant pressure processes are easy to do, but at the same time it remains at constant temperature because it is in a two-phase region. So, what we can do is, in the way in which we were looking at, for example, a TV diagram for a two-phase region for water and steam, we can look at, for example, a TS diagram in a similar way. So, in this case, during the phase change process, which is now 2 to 3, we know that apart from temperature being constant, if I keep pressure, I can keep pressure also constant, because pressure and temperature are dependent variables. So, if I put this Carnot cycle into a liquid vapor dome, I can achieve the isothermal process 2 to 3, which is now also an isobaric process. So, this is one of the modifications we can do in order to try to actually achieve this Carnot cycle. Similarly, process 4 to 1 is also now an isothermal process, but in addition it would be an isobaric process in this case. So, we can achieve this kind of a Carnot cycle by putting this into a two-phase region and using a mixture of liquid and vapor instead of just using liquid or just using vapor. But there are still some issues with this. One of those issues is that in the process 3 to 4, this is an isentropic expansion process. We would expect to do this in the case in a turbine. We can design turbines which work well with only liquid, or turbines which work well with only vapor. It is difficult to design machines which work with a combination of liquid and vapor, where the fraction of liquid is changing. So, here at point 3, we are on the vapor line, this line. So, at point 3, what we have is essentially dry saturated vapor. It is on the vapor line. At point 4, we see that, sorry about that again. At point 4, we see that we are inside the liquid vapor dome, which means that 4 is a mixture of liquid and vapor. So, as I go from 3 to 4, the quantity of liquid keeps increasing, because at point 4 I am far away from this line, at point 3 I am on this line. So, the quality of the vapor keeps reducing, the amount of liquid keeps increasing as I go from 3 to 4. So, this means that there will be droplets which are formed. If I have a turbine which is running at several tens of thousands of RPM, I will have these liquid droplets which will hit the blades and essentially damage the machine. So, what I would like to do is to make sure that at point 4, or essentially through this process, I do not have any liquid at all in the turbine. So, if I want to do that, then the options I have are that one is that I can continue this process 2 to 3 outside, so that I can move this point 4 to somewhere here. So, I want to move point 4 to this point such that it is still vapor at point 4. So, what I need to do is my expansion process 3 to 4, I can now change it here. But if I want to do this now, if I move this point 3 to this point here, I can now have a Carnot cycle. But the whole reason we put this into the dome is because we are not able to do this isothermal heat addition from say 3 to 3 dash. That is going to be very difficult. It is because we could not do an isothermal process in a single phase that we moved it into the dome, and putting this here again means that I have to do single phase isothermal heat addition from 3 to 3 prime, which is very difficult. So, a practical solution to this would be to continue this process from 2 to what was originally 3 at constant pressure. 2 to 3 was already a constant pressure process. I continue this process as constant pressure in a boiler, and I now intersect these here, and I now start, instead of having some 3 dash here, I start this 3 dash somewhere here. So, that I start expansion from 3 dash to 4, which is an isentropic process to some 4 prime instead of 4. This point was 4. I have now expansion from some 3 dash to 4 prime. So, in this fashion what we see is we have changed from a Carnot cycle which was 1, 2, 3, 4, where we had heat addition only at constant temperature, to a new cycle 1, 2, 3 dash 4 dash, where I have some of the heat addition at constant temperature and some of it at constant pressure. 2 to 3 is constant temperature and constant pressure. So, another way of looking at it is that I now have all the heat addition at constant pressure. So, this is one change from the Carnot cycle which we are doing, because it is difficult to design a turbine which can work efficiently with a mixture of both vapor and liquid without damaging the turbine. So, now my heat rejection process, instead of 4 to 1, is now from 4 prime all the way to 1. So, that is another change which we have done. So, instead of Carnot cycle, which would have been only this area, we now have this extended portion also as part of the cycle. We have made the expansion process feasible, we have made the heat addition process feasible, we have also made the heat rejection process feasible. So, there is no problem with that, but we still have a problem with compression. So, at point 1, we see that this point is within the liquid vapor dome, which means we have a mixture of liquid and vapor. We are going to compress this and try to reach point 2, which is at a higher pressure. Now, in this compression process, we are trying to compress a mixture of liquid and vapor, and we do not have devices which can work well with these mixtures again. We can have at some places vapor bubbles which are there, in some places liquid which is there, and so on, and these will again damage the device which we are using. So, what we would like to do again is to make sure that we are either having only liquid or only vapor before we do this process. We would like to do essentially compression in a single phase. We are already very close to the liquid line, because we see that essentially the left hand side of this dome is the liquid line, we are very close to it. So, what seems to be the logical thing is, instead of compressing from this point 1 here, I move to the liquid dome and then I start compressing from a new point which is on the left of the dome. So, I was doing isentropic compression 1 to 2. What I can still do is do isentropic compression from 1. So, I have isentropic compression. I need to compress till I reach the pressure at point 2. If I now draw the isobar which passes through point 2, in the same way in which we are drawing isobars for a TV diagram, what we see is that isobar for this is essentially from some A to some B to some C, D, E. That is the isobar which passes through points 2 and 3 and 3 dash. So, what I can do now is, I start, instead of using this old point 1 here, I start with some 1 prime, compress up to some 2 prime. When I reach 2 prime, I have reached the pressure which is there at both point 2 and at point 3 and so on. So, this is useful for me because it has also another advantage. When I was doing compression with gas, I need to do a lot more work in order to go from 1 to 2. So, if we discuss that if we were having an isentropic process, we had TdS is essentially dH minus VdP. If you have an isentropic process, this is 0, this is our Gibbs relation. So, we have dH is equal to VdP. From the first law, for a control volume, we had the expression d by dt is the heat input minus the work output and so on. So, the heat, if you consider this process from 1 prime to 2 prime to be isentropic, it is adiabatic also if you consider it to be steady. So, then we have essentially d by dt is 0, q prime is 0. So, we are left with W dot is equal to m dot into the enthalpy at the inlet minus enthalpy at the outlet, and we discussed that essentially you can get the work done as integral of VdP. Mod of the work done is mass flow rate into integral of VdP, or the specific work, let me write it as the small w, the mod of the specific work is integral of VdP. So, V is the specific volume, dP is the change in pressure, essentially pressure at 1 and difference between pressure at 2 and pressure at 1. We see that the specific volume is small for liquids. For example, for water it is about 0.001, it is about 1 for, like, say gases like air at atmospheric conditions. So, in case of liquids this V is much smaller. So, the specific work would be much smaller for the same pressure difference in the case of liquids, which is a good thing for us. So, what we can do is, instead of pressurizing from 1 to 2, we are now going to this point 1 prime and pressurizing to 2 prime. So, this is now pressurizing completely in a single phase, in liquid phase, which we would do in a pump. So, after making this change as well as these changes, we are now left with the cycle 1, 2, 2 prime, 3, 3 prime, 4 prime, 1, which is essentially the Rankine cycle which we can use. If we were to expand from 3 to 4, we would have 1, 2, 2 prime, 3, 4, but more commonly we would do 1, 2, 2 prime, 3, 3 prime, 4 prime and 1, where we avoid expansion into the liquid region and we avoid pressurizing or compressing in the liquid region. So, this is essentially the cycle which we have left. So, if we look at this cycle again, so 1 to 2 is the process where we have isentropic compression of only liquid. So, this is liquid phase, this is liquid plus vapor and this is vapor. So, 1 to 2 is isentropic process, entropy is constant. This process would happen in the pump. From 2 onwards, we have a constant pressure process, 2, 2 prime, 3, 3 prime and so on. This is the isobar. So, we have the constant pressure process. 2 to 2 prime is heat addition at constant pressure in a single phase, in the liquid phase. So, we do all of these processes in the boiler, but as a sub unit we have essentially this called as the economizer. So, 2 to 2 prime is the initial heating in the liquid phase, that is shown here. 2 prime to 3 is where we have heating at constant pressure, this is also at constant temperature, and we have change of phase from liquid to vapor. So, that is essentially the boiler itself. And from 3 to 3 prime we are essentially superheating, we are going beyond the liquid vapor dome. So, it would be called as superheating and that is done in the superheater. And at 3 prime we are left with high pressure steam, high temperature steam, we are expanding it in essentially the turbine over here. And we reach, what we would like to do is have this 4 prime on this line. So, we would move further so that we have the 4 prime on this liquid line usually, and then we have we have condensation where we have heat rejection in the condenser, which is essentially this. So, we have these devices as part of the Rankine cycle. We will maybe look at a problem, a tutorial problem where we solve this, but we have essentially some things which we can write in advance. So, if the states are shown like this, more commonly we have this 0.4 prime on the vapor line here, but this figure shows it as slightly inside, but we can have varying positions of this. So, for the cycle with superheat, which essentially means that we are using some 3 prime to the right of this line, what we see is that the turbine work we can get as whatever is the difference in enthalpies. We have looked at the first law. If you take each of these components, like the turbine separately, the condenser separately, pump separately and steam generator or boiler separately, the first law for control volumes is applicable to each of these. We have looked at the first law separately for all of these. So, for the turbine, we saw that the specific work is essentially the enthalpy at the inlet minus enthalpy at the outlet. So, the work for the turbine is enthalpy at the inlet minus enthalpy at the outlet. So, that is essentially H3 dash minus H4 dash if this process is isentropic. If the process is non-isentropic, what we discussed is that when you have a non-isentropic process, we would have the entropy increasing, which means that if I was to draw a constant pressure line through this, the constant pressure line between 1 and 4 prime would look like this, and if this was not an isentropic process, we would start at the same point, we would reach at the same final pressure, but we would reach at some other temperature, and we saw that if I can call this as some maybe some B or something like that, we saw that the isentropic efficiency for the expansion process or the turbine essentially, we saw that it is defined as the actual work which you can get, which is linked to the change in enthalpies divided by whatever you would get if it was essentially an isentropic process. So, that may be applicable to find out the real work. The pumping work is given again as enthalpy at the inlet minus enthalpy at the outlet. So, over here 1 is the inlet, 2 is the outlet. This would be negative. So, if I want the positive value, I should take H2 minus H1. In the pump, we are doing work on the pump because we are giving it shaft work. So, the enthalpy at 1 is less than enthalpy at 2. This is the correct formula, but it would be negative. So, if I want just the value of it, numerical value, I can get it as H2 minus H1. In the case of a pump which runs with liquid, what we saw is that from the TdS relationship, and if we assume that the process is isentropic, we can also get it as integral of V dP. For a liquid, if we assume isentropic and we assume incompressible, then the integral of V dP, we can from the TdS relation we have dH is equal to V dP, and the integral, so H2 minus H1 or delta H would be integral of V dP. If we assume that it is incompressible, then we can take V out of the integral and integral we will be left with the integral of dP. So, if we assume it is incompressible, what we are assuming is that the density is constant or the specific volume is constant, then we can write it in this form, which is essentially what is done over here. The heat input is essentially whatever is given in this process from 2, 2 prime, 3, 3 prime, the heat input which is given in the boiler. This is a constant pressure process. So, from the first law, for a constant pressure process, we have that Q is essentially ignoring changes in kinetic energy and potential energy and so on, we are left with Q input as whatever is the enthalpy of the outlet minus whatever is enthalpy of the inlet, which is what we get from the first law. So, the first law, as these are all flow processes. If I take only the boiler, what we see is that essentially dE by dt is Q dot minus W dot plus Mi dot into enthalpy plus kinetic energy plus potential energy minus the same for the outlet. These are steady state devices in general. I am applying this only for this part of the boiler, not considering that plus this. So, I am applying it for this part of the boiler. So, I have Q dot, there is no work done here apart from flow work, which is already included in this enthalpy, and there are no changes in potential and in kinetic energy usually. So, I am left with Q dot or being equal to m dot into enthalpy at the exit minus enthalpy at the inlet, or essentially small q being equal to enthalpy at the exit minus enthalpy at the inlet, which is essentially this. So, enthalpy at the exit for the boiler is this, at the inlet is here. So, this difference gives me the heat which is input in the boiler. In a similar fashion, Q out is enthalpy at the exit minus enthalpy at the inlet. So, Q H1 minus H4. So, this Q in would be positive, it is heat coming into this system. This Q out would be negative, it is heat going out of the system. And efficiency of the cycle is defined as the net work divided by the heat input. But from the first law, for this entire system, the first law for a system undergoing a cycle essentially tells us that cyclic integral of del W is cyclic integral of del Q, which is what we saw in the beginning of the course when we dealt with the first law. So, this is W net by Q in, but W net is also equal to Q net. So, this is Q net by Q in, and we can write it as Wt minus Wp if I am taking numerical values divided by Q in. So, this is how we would find the efficiency of this Rankine cycle. So, we are going to stop here for the moment, and we will when we rejoin back, we will look at a problem dealing with Rankine cycle. Thank you.